Give me a minute to have my windows all up. All right, so I've pulled up the slide deck from last time. And this is the slide deck we'll start with today. This is topic 4, I believe. Oh, I don't think I uploaded topic 5. I'll do that after the break. Duration and modified duration. So duration in a very, very simple sense. Let's see if I have a price of a bond somewhere. Here, I'll show from this slide. So if we're looking at the 3% yield on this bond, specifically modified duration is the slope of the tangent line at this price point where the yield is 3%. What's the slope of this curve, the blue curve, at that one point? Oh, sorry. And that's the slope of the gray line. So, but it's stated as a percent of price though. So that is the caveat. Stated as a percent of price. So I go back up to these lines. More accurately, it's the slope of these curves, which is percent change in price evaluated at different yields. So for the 3% point, it's the different slopes, because these are all have slightly different slopes. The dark blue line being the 0% coupon, the orange line being the 10% coupon. Now that's important because the steeper the slope, the more price sensitive on a percent basis the bond is to changes in yield. Now the formula for the classic measure of duration, which is Macaulay's duration, that's usually, if someone says duration, assume that they mean Macaulay's duration. The classic measure is this formula. My annotation's out. Which this term right there, that's the weight. And the weight is simply the present value of the cash flow. This is an annual pay bond, annual pay coupon bond. I'm having trouble seeing my cursor. Annual pay coupon bond, discounted, that's the present value. And then you're multiplying that weight times the time, multiply it by the time to repayment. You do it for all the coupons. You also do it again for the final face value, which is received at time t. So if this is a 10-year annual pay, you're going to have 10 coupons and 1 face value, which will be received 10 years from now, divided by the sum of the weights. The sum of the weights is simply the price of the bond. Inventory price of the bond. And so the way that people explain Macaulay's duration, it's the weighted average time to repayment. The higher that number is, the more price sensitive the bond is to changes in yield. Being clear. It is very close to the percent change in price for any given change in yield, but that is modified duration. And all you do is divide Macaulay's duration by 1 plus the yield, and you get modified duration. If you're using semi-annual coupons, it would be 1 plus y over 2. I'm showing you annual compounding, annual coupons. So to apply modified duration, if you have a change in yield, calculate the duration, modified duration for your bond. Okay. This is going through the calculation steps. I believe I did that last time. Is that correct? Four-year, 4%, 6% yield. This is it. Here's the price. Here's the duration, Macaulay's duration, modified duration. So for every 1 percentage point decline in yield, the bond's price should increase by about 3.5526%. And so the bond's yield is 6%. And what if the yield falls to 4.3? That's going to be a pretty significant change. So it will increase change in yield. The bond's yield falls by 1.7%, which is 0.017. Modified duration is 3.5526. So it's going to be 5 to 6% change, a little more actually. Turns out to be a change of 5.6209 per 100 of par. So these are the steps you have to undertake to apply things like modified duration. The point of calculating duration is really just to get a sense for how interest rate risk exposed are you. And so if you look at funds, let me actually pull up a fund here. Let's see. Vanguard duration. If you pull up any bond fund, whether it's an ETF or a mutual fund, they usually tell you things like the duration, the weighted average duration of the actual fund itself. And you see that right here. Average effective maturity is 5.7 years. That incorporates things like embedded options. Average duration, so the weighted average duration, 5.3 years. Yield to maturity, 0.05. So let's see. So for an investor who's wanting to figure out, well, how much interest rate risk exposure does that provide to my portfolio if I include it? So 5.3 divided by 1.00, now semi-annual, so 25 basis points, 0.25%. For every percentage point change in yield, that will be a 5.287% risk to the value of this fund, the net asset value. So if yields go down by 1 full percentage point, I will earn on the market value of the assets in this fund about 5.29%. It actually will be more because of the convexity. It's telling me how much interest rate risk exposure I'm including in my portfolio if I invest in this fund. And most bond funds disclose that. And most bond funds also have some sort of target for their duration exposure that they have to manage. Does that help clarify duration? Is there anything more specific you want me to cover in terms of duration? I think, Jason, that was you that asked. Okay. I can go over it more. I can go over another sample problem that I would just make up. Okay. Hang on just a second. I have to turn off my notifications. A friend in New York is very excited that he's getting to go to the gym. There we go. Okay. It may seem like it's, you know, over analyzing bonds, but it's actually something that is used quite heavily in the fixed income industry. So let's okay. Jason, are you willing to unmute your line and talk
Yeah,
me
that should
through
be
it?
fine. Can you hear me?
Yeah. Yeah, I
All
can
right,
hear
yeah,
you just fine. It seems like it'd be easier if you just
yeah,
go ahead and take
that's a lot quicker than typing that out. So
yeah.
just to use the last example, so in that one we were talking about a 4-year to maturity bond that had a modified duration, I think of 3.56. Yes,
0.552.
Point,
oh yeah, roughly.
So in terms of like real world application, what that would essentially mean is that 3.55?
Yeah.
Okay, so it's essentially saying you're getting 0.45 years worth of interest as profit for your investment at that point. Oh,
no, that's not quite. Yeah, I'm thinking about what you're asking, and I'm trying. So you're saying 0.45 years as profit?
Yeah. So no. if you're repaying your initial investment in 3.55 years, what is the remainder of that? So if the yield to maturity on there is 4 years and it's 3.55, what is the difference between those two equivalent to?
Yeah. So the difference between the effective maturity and the duration is, I don't know that there's actually any use in that. The use in this is if you essentially just put a percent sign on the end of that, that's the percent change in the price for a full percentage point change in yield. That's all it is. It's telling you how interest rate risk sensitive the price is. I don't know that much analysis has been done on, well, if you take the difference between the time to maturity and the duration, if that actually has much meaning or significance to it. But the important part is the price sensitivity with respect to the change in yield. And that's what modified duration is telling you. And modified duration is obviously directly related to Macaulay's duration.
Okay, yeah, the relationship for the price sensitivity makes sense. I just was wondering if because we're essentially expressing that in almost like a length of years, if that had any significance.
Yeah. So that is the peculiar thing about it, and it really has to do with Macaulay's duration. That's the one that's expressed in years. So you would oftentimes see duration 3.766 years. And then you would have to know, well, that's duration. I need to change it to modified duration. So what's the effective yield? And that's why over here you can see effective maturity, average duration, 5.3 years. And so when I saw average duration 5.3 years, here are all the fields, all the drawings. 5.3, it says average duration. So since it does not say modified duration, I'm going to presume that that is actually Macaulay's duration. So 5.3 divided by, and for a semi-annual pay bond, you have to divide the yield by 2. So rather than 1.005, it will be 1.0025, because all these bonds, they're government bonds, they're semi-annual pay. This is the modified duration. So if my yields, so for some reason, yields on average all increased by 1%. Oh. Times 0.01. All increased by 1%. My expected price change would be a 5.29% decline in price value. My market value would fall. Since they put average duration as 5.3 years, that's another indication that they are using Macaulay duration, because modified duration would more likely have a percent sign next to it. So these are the ways that duration is used for bond analytics. And it's also similar to something that's used more broadly, which is called DV01, dollar value of an 01. 01 meaning 1 basis point, 1/100th of 1%. And that's used more broadly across all fixed income, including for things like corporate bonds and credit default swaps. It's also used for interest rate swaps. So duration is the weighted average time to repayment, measured in years. Modified duration is the percent change in price for any percentage point change in yield. there any further clarifications that I need to make on duration? It is an important topic. If we talk about fixed income and it's something like this, that is definitely something I want you to be able to leave this class from, and you might not be able to necessarily calculate it from scratch without looking at a formula, but you will understand what it means. Just to help clarify the point, I'm going to do so that was intermediate term. I'm going to go to long term. Average duration, 18.4 years, 1.7%. So that other VGIT, which was a 5.3 year average duration, turns out to be a 5.29% modified duration. So every percentage point change in yield is a 5.29%. Let's take 18.4 divided by 1.00, that would be 85. 1.7 divided by 2 is 0.85. A 1 percentage point change in yields across the board of all maturities for this fund. If yields increase by 1 percentage points, you would lose 18% of your value. It has a higher duration. It's far more interest rate risk sensitive. What if we do choose your ETFs? If I can do a search on here. Vanguard has one called EDV. Extended Duration Treasury Fund. Remember I talked about STRIPS, separate trading of registered interest and principal securities, which are essentially zero coupon government bonds? 24.3 years effective average duration. 24.3 divided by 1.0095. 1.9 divided by 2, because it's semi-annual, is 0.95. 24%. A 1 percentage point increase in yield would result in a 24% loss in your investment. Price impact. The larger the duration, the higher your interest rate risk exposure. Interest rate risk is how much does your market value change for any given change in the yield or interest rates. Unless there are questions, I'm going to move on from here. Okay. All right, I think where we stopped last time, we stopped at convexity. And so I'm going to pick up here. Trying to think. I actually created the, so does, oh, that's not what I wanted to do. Does anyone want me to open up the quiz to be due on Sunday morning to give you an extra attempt? I'm happy to do that. The purpose of these quizzes is this is kind of a mess up on my part because I didn't post it before spring break. Does anyone want an extra chance to take the quiz? Because if you don't speak your mind now, I'm going to go through the quiz, and that will essentially make it so that you cannot take it again. Okay. All right, I'll go in and modify the quiz so that you can, I'm assuming that you have not, those that want to take it, you have not taken it the full 3 times. So I'm not going to change the number of times that you can take it. But I will extend the deadline to, I think, Sunday morning, or Sunday evening. I'll also post a quiz for quiz number 4. So I will not go over the quiz today. I'll go over that next week. Okay. All right, convexity. I had a typo here. This P, the third P on this equation was missing. All right, convexity is, those of you that remember calculus, it's telling you that there's a curvature to the line. I've already gone through that, but it bears mentioning again. Duration is the slope of that curve at any specific point in percentage point terms, percentage point change terms. Convexity is how quickly that slope changes. This is important because when we try and estimate, well, what is the expected change in price if yield changes by X percentage points and modified duration is Z? You're going to be wrong. You're going to be off. You will underestimate, actually, always, the change in price. And so to adjust our estimate, sometimes we will be given, well, here's the modified duration, here's the convexity. And then you have to figure out, well, what does that actually mean? Now, I'm not going to make you calculate convexity, because again, that's more of me testing you. Can you use a calculator? But you do have to understand the convexity adjustment. What is the need for the convexity adjustment? And that is important. I won't make you calculate convexity, but I may make you calculate the expected change in price with the convexity adjustment. So you don't need these formulas. I will give you convexity, but you will need to know how to apply it. So here's that graph again. This is price, not percentage change in price. If I were actually doing this the way that it's supposed to be done, it would be log bond price. Natural log bond price is the best way to show it, but that makes it linear. So here we have our bond evaluation at a yield of 3%. That's that dot on the line. The duration, the modified duration, is essentially telling you, okay, we need to move along this gray line here to figure out what the change in price is. What will the new price be if yields go down to 1%? And so look at that point. Look at 1%. It's right around there. We're moving along the gray line when we do our duration adjustment. We're below the blue line. So we're underestimating the actual price. What if we go over, what if the yield goes up to 5%? And I'm using very big yield changes because that way you can actually see. Well, we're still moving along the gray line. We're, again, below the blue line. It has to do with the convexity of this blue function. It's not a line, it's a function, it's a curve. It is convex. It is bowed upwards. So when we're using this point of tangency, as they call it in calculus, to estimate where this price will move for any given change in yield, we're always going to underestimate. We're always below the actual price. But the point of it is not to actually, we're trying to get an accurate estimate. The point of duration and convexity is to give you a sense for your interest rate risk exposure. And if you're hedging using various products in financial markets, like bond futures, interest rate swaps, you can also estimate how much residual convexity exposure you will have if you're using instruments to hedge your interest rate risk exposure. And so yes, in an academic setting, we collectively as professors will test you. Can you apply duration? Can you apply convexity? But the important aspect is understanding why practitioners will actually take note of, well, what is our duration exposure? What is our convexity? Because they might actually be trying to hedge some of those exposures. I have a friend of mine who's an equity investor, and he doesn't even hide the fact that he doesn't really know much about bonds. But someone once said to him, he botched, I think, re-saying it, but duration is how much money you lose, and convexity is how quickly you lose it. And he thought it was great because he said, I never really understood what duration and convexity are. And just so I'm clear, that's not what duration and convexity are. The person who told that to him was actually a bond investor, and said that kind of like as a joke. But anyway, just a little aside. That's bond humor, which is very close to economist humor. So they're right next to each other on the spectrum of funny things that aren't really funny. Anyway. How can you actually apply convexity? And those of you that are interested in taking the CFA examinations, I believe this is still part of the curriculum. Understanding how to apply convexity. If they give you a bond with semi-annual coupon, and they specify the coupon rate and the maturity date and the duration or modified duration and the convexity, you would have to then use that to find the answer. And the way that it works is using this formula here, essentially. Estimate the price of a 10-year 3% coupon bond trading at 104.25. That's a 2.5% yield. If the yield increases to 2.75%, modified duration is 8.6387. Convexity is 98.3. This topic 4 now? Or are we still on topic 3? I can't remember. I think this is topic 4. So, just to make it easier for my calculations, I'm going to do this. Change in price is equal to negative modified duration times the change in yield plus, let's go back to my formula, convexity, so I'll just use C, See if this works. I always hope that it doesn't. It never does. Ah. There's my convexity adjustment. Right, modified duration, 8.6387. 8.6387. Change in yield. So we're going from a 2.5% yield to 2.75% yield. So that's 0.0025. 25 basis points. It increased by 25 basis points, which means that the bond price will fall by some amount. We're always going to be below the actual price change, so our convexity adjustment what's convexity? 98.3. Okay. 8.6387 times 0.0025, 2.15 some change. And remember, always remind yourself, yield went up, price is going to go down. So leave that negative sign there. We'll do 2160. Close enough. Now, 0.0025 squared divided by 2, very small number, times 98.3. .1 basis points. Just because it's such a small number, I'll add that. I guess to be fair, 8.6387 times 597. Keep the same number of significant digits. I'll do it again with one less significant digit to see what that would be. 0.021597 negative plus 0.00031. So again, that 3.1 basis points, 3/100ths of 1%. And again, it might not seem like a lot, but when you're adding 9 zeros to the nominal amount or the par value of bonds that are being traded, then it actually becomes a meaningful amount of money. So, what's the price? Let's see, where was the 104.4? Okay. Plus 1 times 104.4, 102.178. See how we did. All right, let's see what's today's date. Actually, we just do it this way. Better see it. Is it, did I say semi-annual or? Okay, I'm gonna presume it's annual. %3 coupon, 2.75%. $102.160. We're still off. But notice what happened. Our estimate, if we only use duration, we only use the modified duration, we will always underestimate. We will always be below the actual price. Adding modified duration, it actually over-adjusted. Our estimate using, including the convexity adjustment, including the convexity adjustment, we overcompensated now. And so now we have overestimated the price, but we are closer. If we had not used that convexity adjustment, what would it have been? 1 minus 0.021597 times 104.4, 102.14. It's 102.177. So we are closer. But as you can see, that's magnitude-wise, not that big of a deal. As you have larger and larger yield changes, the convexity adjustment will be much, much closer. As you're estimating larger and larger yield changes, your convexity adjustment will get you much closer to the actual price. Okay. This goes through what I just did to a higher degree of precision. 2.129, what did mine have? 2.1287. So pretty close. All right. Any questions about convexity? I can guarantee you I'm gonna put a question on the quiz. At the very least, where you have to calculate using convexity. Definitely you're going to want to know what convexity is, how it works, what it means. Okay. Let's talk about par versus spot yield curves. So a yield curve, if you go into the field of anything that has to do with financial markets and you touch on fixed income, you're absolutely going to need to understand the difference here. A yield curve in general is just a menu of interest rates where you have essentially your borrowing or lending interest rate for every associated term point or maturity point. Now, I've worked with people who prefer to look at their yield curves like this. Now, look at the x-axis. These are category x-axes: 1 month, 3 month, 6 month, 1 year, 2 year, 3 year, 5 year, 7 year, 10 year, 20 year, 30 year. These are the very common term points you would see on a Treasury yield curve. Now, I want you to look very closely at this graph and realize that the x-axis is not to scale. It's not scaled by time units. It is simply bucketed by categories. Now, I have always preferred to look at this yield curve where I'm going to show you the same yield curve. So keep your eye on it as I flip to the slide to the next, flip to the next slide. I'm going to show it to you where it's done as a scaled, measured in years, more like an XY graph. Okay, I'm going to turn the slide now. The same yield curve. But I've changed the scale of the x-axis that it's no longer bucketed by categories. It is now represented as years to maturity. How different it looks when you do that. It's really a matter of preference, and my preference is this format, because it gives me a much better sense of how long you have to hold this investment to get that extra little bit of yield. And it also gives you a better sense of that, things like what's called the roll. As you roll down the yield curve, you can see that the roll accelerates around the 2 to 3 year point. The curvature increases materially. These are par yield curves, which essentially is saying what coupon rates would these bonds need to be issued at for them to be trading at par right now. So that's a par yield curve. Essentially, what's the current on-the-run yield? That's what this is showing you. But there's an aspect to financial markets that I think is important for you to understand. These are just a comparison of what the 2010 yield curves look like if you do that bucketed on the left or my preferred on the right. Those two shapes look very different to me, and I prefer looking at yield curves like I have on the right. Okay. Now, we're going to use these par yield curves to do something called bootstrapping at the end of this presentation. That's turning interest-bearing estimates to I have a question here. Is the y-axis yields or coupon rates? For a par yield curve, they're one and the same. But always assume yield. A par yield curve, the yield and the coupon would be equal to each other. But always, when you're looking at yield curve graphs, I always assume that it is the yield, because that's more informative to me. So, okay, good question. Yeah, I didn't label the axes. So it seems like this is a trivial thing to be looking at, but it's actually a huge part of financial markets. And if you are looking at, if you have interest in FX markets, foreign exchange markets, really foreign exchange markets trade on interest rates. It's relative interest rates that are really moving foreign exchange markets. A spot yield or a spot rate is different from the par coupon rate. The spot rate is the rate for a single cash flow instrument. So a 20-year spot rate is the rate for a zero coupon 20-year cash flow. Zero coupon. Let's see. Now, there is an important thing to understand here. There are aspects about the yield curve, and the book goes through this. I don't know if I enumerate them in my slides. I don't think I do. But I will include them in probably include them in quizzes, because I think they're important. Let's see if I can find them in the chapter. But it has to do with things like term premium. I think I do list them in here. Market segmentation theory. All these things that are aspects of interest rate markets. But right now, what I'm going to present to you is, let's assume that the spot yields are a perfect market pricing of zero coupon rates in the expectations hypothesis world. They're telling us what the market is expecting over the whole life of the yield curve, the entire horizon. So if it's for 30 years, it's telling us the 30-year horizon expectations for interest rates. So the bond yield is shown on that first equation. So this first equation is calculating the dirty price using the bond yield, that specific bond yield. So it's just a Y there. The second equation is not using the bond yield. The second equation is using all the different spot rates. So if this is a 10-year bond, it has one yield, but there are 10 different spot rates. One for 1 year, one for 2 year, one for 3 year, 4 year, 5 year, all the way on to 10 year. There are 10 different rates to keep track of. In the market expectations world, these two values will be equal to each other. Now, from looking at bond yields, from looking at bond pricing and specific bonds, we can actually calculate, well, what's the implied interest rate? Looking at the spot rates for 1 year and 2 year, what's the implied 1 year interest rate that starts 1 year from today and matures 2 years from today? What's the implied interest rate that starts 9 years from today and matures in 10 years from today? It's a 1 year instrument, but the start date is 9 years away. So we're going to use an example where we're using banker's discount rate. It's important to know banker's discount rate. I will tell you, banker's discount rate or compound. So here we're going to do banker's discount rate. We have a 3.5% 3-month rate and a 3.65% 6-month rate, both 30/360. on a discount basis. If you borrow 6 months and simultaneously lend money for 3 months to one counterparty, and then you have someone else, another customer says, well, I want to borrow for 3 months, but not now. I want to start in 3 months and pay you back 6 months from today. So their 3-month period doesn't start until 3 months from today. What's the interest rate I could quote them? Has anyone ever worked a problem like this? Okay, I guess we can use we know how to do the day count, I think is what. So this is a fundamental part of fixed income markets and foreign exchange markets. On the left-hand side of this equation, I have my 6-month borrowing. On the right-hand side of my equation, I have my 3-month lending for the first 3 months. Then I have my 3-month lending for the second set of 3 months. If this is a market expectations hypothesis kind of world, or market expectations theory, I think is what it's called, then I should not have any kind of opportunity for arbitrage profits. My net present value of each of these, whether it's borrowing 6 months, lending in 2 sets of 3 months, or lending 6 months and borrowing in 2 sets of 3 months, I shouldn't have any arbitrage opportunity here. So these two terms on either side should be equal to each other. And so if you work through the math, you end up with a 3.767% interest rate, 3360, that you could quote client who wants to lock in a 3-month borrowing cost or deposit rate that starts in 3 months' time. This is called the forward rate. And there is an enormous market for forward rate agreements in nearly every major currency zone. They're called FRAs, FRAs.
Professor?
Yes.
Just a quick question. So isn't there inherently risk in guaranteeing somebody an interest rate for a future period? And would you not include some factor to mitigate that risk?
What kind of risk? Lots of risk.
So say we did quote someone, all right, in 3 months, I'll lend you money at 3.767%. Mm-hmm. And at which point, like over the 3 months, the market interest rate goes up. Mm-hmm. So effectively, you've lost money by guaranteeing them that rate. So yeah, if that's a risk that you're taking on by locking in that rate today, is there not a way to mitigate that risk in the pricing structure?
So think about it from a broker-dealer perspective, because that sounds like the question you're looking for, and that's the perspective you're looking at. So a broker-dealer is making a market in forward rate agreements, interest rate, forward interest rates. So they would look at where they can get their 6-month and 3-month interest rates for today. And from that, they can lock in their rates by acting in markets. And then they can sell to clients, oh, do you want a deposit interest rate from 3 months to 6 months, or do you want to borrow from 3 months to 6 months? And then they will quote them a bid ask. If you want to borrow, it's going to be 3.773. If you want a deposit, it's going to be 3.761. And so they get to make, what did I just say? 3 cents. 6 in either way. So 1.2 basis points bid-ask spread. But they've, through their transactions that they're doing, whether it's borrowing 6 months, depositing 3 months in the open market to provide these 3-month to 6-month forward agreements, they're making that 1.2 basis point spread on the making the market revenue. But they're completely locking in their interest rate risk exposure, so they don't care what happens to interest rates between now and 3 months from now. So they create a set of transactions that have completely mitigated their exposures to interest rate risks, and they simply quote bid-ask spreads to their clients, who then the client then decides they want to borrow or lend. They want to borrow or deposit for that 3 to 6 month period. Does that answer your question?
My audio is breaking up a bit, so I'm probably gonna have to rewatch that. But I think you did, yes.
Okay. Okay. If it's still not clear, send me an email. Attend office hours. I'll go through it again. But essentially, what this equation is used for is for broker dealers to essentially lock in, whether they are depositing 6 months, borrowing 3 months, and then, borrowing from 3 to 6 months time, or vice versa, and making a market and adding a little bit of a bid-ask spread on this interest rate you see here, this 3.767%. So you will borrow on one side and lend on the other side of the equal sign. But you could very easily do the opposite. From the standpoint of the broker-dealer, they're making the market. So the client can essentially choose, they want to, let me use my annotations here. The client is deciding whether they want to borrow or lend from this point, from 3 months from today to 6 months from today. That will determine the interest rate that the broker-dealer quotes them. And they won't just quote them the one, they'll say, here are our bid asks. Here's our bid and ask for the 3-month, 6-month forward interest rate. And they use market transactions to lock in their interest rate risk exposure. So it's not lock in, mitigate, completely cancel out their interest rate risk exposure, and they make revenue on the spread of the bid ask. So they determine their rate from the rate of them borrowing from another firm. Mostly these are going to be open market, but yes, essentially. So they're using open market transactions. Okay. I'm going to continue unless there's another question. Okay. We're going to do the same problem, but we're going to use a compounded method. Excuse me. And this is where it gets a little tricky. Those of you who haven't done power functions in a while, this is going to be a bit of a memory jog for you. So on the left-hand side of the equation, I have the 6-month product, half a year, 3360. On the right-hand side, I have the 2 3-month products, quarter of a year, 3360. Whether I borrow 6 months and lend for those 2 3-month periods, or borrow for those 2 3-month periods and lend for the 6-month period. Either way, these two sides of the equation need to equal each other. If you raise everything to the power 12, it gets rid of the 12, and then raise everything to the power 1/3 after that, this equation is equivalent. Does anyone want to see that worked out each step? Now it's just a matter of solving for what this interest rate R, this forward rate, 3-month, 6-month forward, is what you most likely would hear someone in this specific market call that. It starts in 3 months, matures in 6 months. 3.8002%. That's a forward rate. If you have a lot of spot rates, you can essentially calculate the market implied forward rates for as many points as you have access to. And this may seem, again, like it is tedious. A lot of tedious steps. But it's actually some of the largest markets use calculations like this. Compound mechanism is not necessarily more accurate, it's a different convention. It's simply a different convention. It's like inches versus centimeters. Okay. So we're going to go through an example called bootstrapping, or example of bootstrapping. So when the market gives you pricing, they're going to give you pricing based on coupon-bearing instruments. And broker-dealers turn those prices and coupon yields, par coupon yields, into zero coupons or spots. And then they can sell spots, they can sell forward rate agreements. If they do this across different currency zones, they can sell forward foreign exchange contracts. Let's say a client has a need to transact and exchange US dollars for pound sterling in 6 months' time. And then they're going to need to exchange those pound sterling or some pound sterling 6 months later back into US dollars. That's called an FX swap, foreign exchange swap. It's two paired FX forwards. US dollars to pound sterling and then pound sterling back to US dollars. They use these calculations to determine what the exchange rates are. We don't go through that in this class because we don't cover FX markets in this class. It's just an example of where people use these. So, forward rate agreements, interest rate swaps. In order to price these, we need to have spot rates and forward rates. So we need to use a technique called bootstrapping. Now, those of you that have studied statistics, this is a different kind of bootstrapping. We're going to use these two equations. We're going to say they equal each other. And so we have to go through each one of these. So what I'm going to do is I'm going to price the forward rates, 1 year, 2 year forward, 2 year, 3 year forward, 3 year, 4 year forward. That's the 1 year interest rate that goes from the end of this year to the end of next year. The 1 year interest rate that goes from the end of year 2 to the end of year 3. The 1 year forward interest rate that goes from the end of year 3 to the end of year 4. And again, I could do this on a 3-month basis. I could do this on a 1-month basis. But the point is not me trying to test you on being able to do all these tedious calculations. The point is me trying to show you what a forward rate is. Because you're not going to need to calculate these if you work in financial markets. There will be a lot of tools that are made by very advanced programmers, much better than I ever was. But you do need to understand what they mean. So first of all, what's the 1 year spot rate? That's where we have to start. Anyone want to do it really quickly on their own piece of paper and tell me what the 1 year spot rate is? Easiest one to do. What's the zero coupon interest rate for 1 year's time? Simple. Yeah. The first spot rate is always the easiest because you're usually given a zero coupon instrument. It's just 1.92. No calculation required. But then once you get to subsequent spot rates where you have coupon bearing instruments, then it becomes a little trickier. So let's start with the 2 year. Remember these equations. The inventory price is equal to the discounted cash flows using the bond yield, which is constant and it's given here. It's also going to be equal to the discounted cash flows using the separate spot rates, the zero coupon rates. So set these two equal to each other. On the left-hand side, it's using the bond yield, the 2 year 5% coupon, 2.52%. 5% coupon, so 5 in 1 year cash flow. The second year cash flow is 105. Both are discounted using the 2.52% bond yield. On the right-hand side of the equation, we have those same cash flows, but this time they're discounted by the spot rates. And we only have the 1 year spot rate. We do not have the 2 year spot rate. So you solve, end up with 2.5347%. Great. What's the 3 year spot rate? Again, left-hand side is discounting using the bond yield. The right-hand side is discounting using the spot rates. The only unknown we have is the 3 year spot. It just becomes a giant algebra problem. 3.0788. And we continue to go on forward. What's the 4 year spot rate? Our equation is getting very big. Imagine if we were doing this using semi-annual coupons. It's a lot of work. look at how the yields and the spots don't match up perfectly, but they're very close to each other. So you might be thinking, well, what's the big deal? Couldn't we just use 3.52 and 3.06? Let's see. 3-year yield, 0.06%, 3.52. And then 3.0788. If we were to use the plain yields and we were to say, you know what, I'm just going to use those and I'm going to get my forward rate using those. Remember, essentially that formula, 0.0352 to the power 4 should equal 1.0306 to the 3 times 1. See if I have a good. There we go. Now we need to solve this. That's the fun part. So what I have on the left-hand side here is that 4-year product. On the right-hand side of the equation, I have the 3-year product plus the forward rate that goes from the end of year 3 to the end of year 4. Remember that those two values need to be equal for this to work out. Otherwise, there's an arbitrage opportunity. .14841. Again, I'm using 5 degrees of precision this time. But I try when I make exams and quizzes to use fewer degrees of precision. Did I do that right? When I'm typing in the answers, just because I'm not trying to penalize you. 464. So why can't we just use this? I'm sure that's pretty close, right? Compare it. I have to replace all these, so that's 3.5955. 0788. Oh, 35955, power 4. 5176. I have to change that. 30788 cubed. That's at a 5, 2, 4 rounded. .161%. This is the number you're supposed to be using if you're trading in forward rate agreements. If you don't do the bootstrapping and just use the bond yields, you are off by 25 basis points. It's this amount in decimal points. What if you had a client come in and say they wanted 500 million? You're off market by a 1.25 million amount. So that's why. Market pricing says you should be using this 5.161 if you're using the spot rates. If you take a shortcut and say, well, I'm just going to use the yields instead, and I'm going to use 4.912, I'm going to skip that whole bootstrapping exercise because, I mean, really, this is way too much calculation. It means real money. So. Okay, maybe. So if spot rates have 0 coupons, then why do we use the C over 1 plus RK or the K term in the right side? Ah, yes. The spot rates are telling us the single cash flows. Let me go back up. I can use any of these. So the 4-year, because there's a lot in there. Okay. The spot rates are telling the discount rates for a specific point in time. So this 1.92 here for 1 year, that's specifically for a 1 year ahead from now cash flow. The 2.5347% for 2 year, that's specifically the discount rate only for a 2-year ahead cash flow. Same thing for that 3-year spot rate. The bond yield, by comparison, is more like telling us kind of an average discount rate that equates to be the same price value. So we have an average discount rate that works out to get the same price as opposed to the specific cash flow timing discount rates. So that's good enough to get a price and a yield. But when we're looking at, okay, well, let's figure out what the interplay is between all of these different timings, we need to use those spot rates that are specific to that period of time cash flow. Yes, that's why it's called the spot rate. It's that specific spot of time, that specific spot of the cash flow. I've never thought about it that way. I've just always just called it spot rate. But yes, that's absolutely. It's telling you exactly the discount rate for that exact cash flow timing of a single cash flow. So any other questions about bonds? Because I think we're now through the fixed income part. We are going to get to actual, investment theory, but this is laying the foundation of the different products and how they interplay. Okay, let's take a 10-minute break.